Welcome to Unit 3. This is looking at energy and fields. So the first thing we're going to do is we're going to talk about a type of energy we didn't do in grade 11, which is elastic energy. Um, Elastic energy is basically that a lot of objects have what we call a restorative force, that when they're removed from a rest position, they can exert a force against the object moving them. So either if they're compressed or if they're stretched, they exert a force proportional to how much they're stretched or compressed because they want to go back. Basically, it's a lot like physical chemistry, where objects want to remain at an equilibrium point. They have an equilibrium point, a space that they like to, basically a size they like to be. So examples are things like diving boards, trampolines, rubber bands, springs, anything that basically when you stretch them or compress them, they get a force that pulls them back to their initial shape. Now, the nice thing is, most things follow something called Hooke's law, named after the guy who invented it. Well, didn't invent it, he discovered it. So that within most regions, what we call the elastic region, the relationship is actually linear, up to something called the limit of proportionality. So when you stretch something, it's usually about the same force required to stretch it a certain distance until it gets to a point. And then once it gets to that point, it's still elastic, but it's not linear anymore. Think of stretching an elastic band. Really easy, then it gets harder and harder. Then you hit what we call the plastic region, where it gets permanently deformed. So we've all done that with a spring. You've pulled it too far and it won't go back. And then eventually you get to the point where it'll fracture. It'll actually break. But in most regions, and especially when we're designing something for work, we want to keep it in that elastic region. It actually creates a linear equation where, following Hooke's law, where the force is proportional to something called the spring constant times the distance in meters that we've stretched it. So you actually get a line. By the way, the fancy words for the force is called stress. The fancy word for the stretch is called strain. So for most things, it actually would be linear. So the first thing we need is a sign convention, because keep in mind things like springs can be stretched or compressed. So we can have a change in position, a delta x, in two different directions. So by convention, what we say is, if the string is stretched, both delta x and f would be positive. So if you're extending the size, we call that a positive delta x. If you're shrinking it, we call it a negative delta x, okay? So a positive force and a positive stretch would be in this direction, making it bigger. A compression would be a negative force and a negative delta x. That's just the sign convention that we pick. So for example, let's say you take a spring with a force constant of 48 Newton meters, and you hang a 250-gram mass from it. By the way, this is what we do when we're normally in class, although I don't think you guys have math sets and calibrated springs at home. So we're going to do this online. So if you stretch a spring by applying a certain force, we can predict how much the spring is going to stretch. This is why springs are really, really useful in mechanics and for making us, and to actually do things with. Because if we know the spring constant and we know the force, we can predict how big it's going to be. So F is K delta X. Delta X, remember that's the reason we use the delta is that's the change in length. That's not the total length of the spring. That's just how much the spring's length has changed from the force. Delta X is F over K. The force in this case is the force of gravity, which is just mg. Divided by our spring constant, you get 0.051 meters. So we know that spring is going to stretch 5.1 centimeters. So this is how we can actually predict, we can pick a spring for a job. That's why springs are really, really useful, because we can predict the forces and we can predict the stretches that they're going to have. And keep in mind, it's exactly the same for compression, except compression will be a negative force, which would actually create a negative distance when we calculate it. So this also creates energy. So if we look at the length versus the load, basically, we get that straight line. And that's the work done. Remember, work is force times displacement. So force times displacement gives us work. Work is change in energy. So, and the nice thing is, because it's a straight line, the area under it has a shape that we know. It's a triangle. So it's 1/2 base times height. So in this case, the base is your delta x, the height is your force, which we know force is k times delta x from Hooke's law. So it works out to the elastic energy is 1/2 k delta x squared. By the way, this really looks like kinetic energy. Be careful when you're putting them together. This has a k, not an m. You can't cancel the masses when you have kinetic and elastic because they're different constants. For kinetic, it would be the mass. For elastic, it's the spring constant, which, by the way, is a constant I'm always going to give you. So the elastic energy is the energy in potential stored in joules. K is the constant. Delta x is how much we've stretched or compressed the spring. So a useful thing of this is basically like why we have crumple zones in cars, is it dissipates the energy. So let's say you have a block of mass 2.5 kilograms sliding across a table and it hits a spring. Okay, it's moving at 3 meters per second when it hits a spring, and we want to know how much does it compress the spring, because ideally we want the other car to stop before it gets to where you are in your car. So what we do is we know the block has kinetic energy, we know conservation of energy, we know the kinetic energy before. For it to stop has to be the elastic energy after. Kinetic energy is 1/2 mv squared. Elastic energy is 1/2 k delta x squared. So we basically rearrange that for delta x. So divide by k, take a square root, plug in the numbers for the mass, the velocity, and k, and we find that our spring will depress 25 centimeters. So at the beginning you have kinetic energy of the moving block. At the end you have elastic energy of the stopped block, because the block is now stopped, it's got no kinetic energy, but it's given that energy to our spring. Now, by the way, this would be minus 25 because it's compressed. Keep in mind, when we take a square root, it gives you plus or minus, so that answer is actually there. It would have the same effect stretching a spring or compressing it. It's a magnitude, which is what energy is. So that's a typical question with elastic energy. Really easy to use. What I'm going to get you guys to look at is how does it move in a little more detail. Now, by the way, a cool thing about this is you can use a spring, if everything is perfect, to create what we call a simple harmonic motion with a period and with a frequency. So if we left that spring alone, what would happen is it would eventually bounce back and it would stretch until it had, so it would convert all the energy back to kinetic, but then as it started stretching, it would convert it back to elastic again, and it would stop it, bring it all the way back, and you would eventually get it oscillating back and forward in a steady state in a simple harmonic motion that if you were to graph, the position would actually look like a sine or a cos wave, which is kind of cool. Because the total energy has to stay constant. It was the block coming in that gave it the energy, but that energy has to stay constant. So we call that simple harmonic motion. However, in the real world, this isn't going to happen because there's going to be friction. So some energy will be lost to the ground to friction. So we get what would actually happen is it would be damped. So damped harmonic motion means you're losing some energy to outside work, and the stretch would eventually get less and less and less until it. So this is what the real world would look like if there were friction basically taking some of the energy away. But we can describe all the energies, and if we know the friction, we can figure out the damping. And this is why springs and elastic devices are really, really useful to us in the real world, because all this math can be calculated. We can figure out how fast it's going to go back and forth. We can find the period of how fast the spring goes back and forth, which is why we use springs in watches. No, we used to when we made mechanical watches. So the math of springs is very simple. F equals k delta x, and E equals 1/2 k delta x squared. But what you can do with it, the power, is actually really, really quite incredible. All right, thanks a lot. See you next time.